Okay, good morning. All right, let's continue what we've been doing. First of all, exam reminder, next Tuesday, 1 p.m., all of music, same place. Be sure you know where you're going. Same place as last time, okay? 1 p.m. Tuesday. Don't forget. Also, I came across this article the other day. It's about preparing for stressful exams. So anyway, this article, you can read it if you search for it, but I'll give you the short summary. It says that people are very bad at retrieving information under stress, which is understandable, and no one questions that. So what they actually found out is that if you practice taking exams, it makes you better at taking exams. So what this means is that you want to duplicate the stressful conditions from a real exam. For example, the time constraint, and also you're all on your own. So what you can do for your exam on Tuesday is that once you feel you're ready, print out one of the old exams that you have not seen and time yourself 2 hours, no outside help whatsoever, and just do it. It gives you one more chance to practice that information retrieval under stress. And at the very least, it should be able to tell you the kind of mistakes that you're likely to make under stressful conditions. You can do something about those mistakes, or at the very minimum, you know about those mistakes. So on your real final exam, when you have time at the end, you can look back and try to look for those mistakes that you have seen. So I'll email this article to you after the class today, and you can read it. But the short story is that duplicating that stressful condition as you prepare for an exam turns out to be very beneficial. Okay, now back to what we have been doing. Looks like the first one on the list is number 53. Question says, use Stokes' theorem to find a double integral of the curl of some field ds, where the field is given by this equation, x squared EYZ I plus y squared EXZ J plus z squared EXY K. And the surface we're talking about is the hemisphere. Upper half of a sphere, radius 2, oriented upward. Okay, just a glance at this field here, you know you really don't want to deal with this kind of thing. You got to take the curl of this first and look at all these x, y, and then e and all that stuff. That's going to be a huge mess. You really don't want to do that. And that's why Stokes' theorem is the way to go. And the problem even says to do this with Stokes' theorem. All right, so remember what Stokes' theorem says. Stokes says that instead of doing the double integral of the curl, we could simply do a line integral of f dot dr, where C is the boundary curve of the surface S. And the only other thing that we have to really watch out for is the orientation. Okay, so let's see what we're doing here. We have a sphere, radius 2, just the upper half. we go. That's 2 and 2 and 2 here. And we're told that the normal vector is oriented upward. The boundary, now this is it's like a contact lens, basically, right? The boundary is that circle at the bottom. This guy right here, this is our boundary curve. That's where the surface ends. That's the boundary. All right, so which way is that thing going to be oriented? If we look down on it, from top down, which way is that going to be oriented? Counterclockwise, right. Remember, by the right-hand rule, that's how we figure this out. Also, there's the other thing that if you're walking along that contour curve and your head is pointing in the same direction as the normal vector, then that region enclosed by the curve should be on your left. All right? So that's the only way we can make that happen. So here we have a counterclockwise, and that's important. Next thing we need to do is to parameterize that curve. Okay, so looking down, this is what we see. Circle of radius 2, oriented counterclockwise. So the easiest way to do that is that, right? R cosine theta, R sine theta for x and y, and z, we're sitting on the xy plane, so z is a 0. And we want t to go from 0 to 2 pi. So it starts here and where it started. Okay? Now dr is just the derivative of this with respect to t minus 2 sine t, 2 cosine t, 0 dt. Okay, now we got to rewrite our field. Okay? All right, so what do we see here? We see x squared e to the yz. So we're going to be looking at the curve here. X squared is 4 cosine squared t, right? That's our x squared. Then e to the y times z, e to the 2 sine t times 0. Second component, y squared, 4 sine squared t, so that's y squared, that's e to the yz. And then we have e to the xz, 2 cosine t, 0. And these turn into 1, right? So we don't have to worry too much about them. Last one, z squared. And if z is always 0, this last component will go away. So 0 e to the, it doesn't really matter anymore because that's 0 there. But I'll write it out. Okay, so we end up getting 4 cosine squared t, 4 sine squared t, 0. Then we're going to integrate f dot dr. You dot this with that. Zero 2 pi f dot dr, 0 2 pi. First component of f is 4 cosine squared. We're going to dot it with the first component of dr, so that's negative 8 cosine squared sine, right? And then the y components, we're going to have positive 8 sine squared cosine. There are no z components, so there's no last part. They look almost the same, but they're not quite. But both of those can be integrated by substitution. First one here, I'll let u be cosine. Second one here, I'll let u be sine. Okay, so when I integrate this, I'm going to change the integration limits to refer to u. Cosine of 0 is 1. Sine of 2 pi is also 1, right? What happens when your upper and lower integration limits are the same? 0. It doesn't matter what you're integrating. So I'm going to integrate something, whatever that is. I don't really care because of these two things being the same. Same thing here. U sine of 0 is 0. Sine of 2 pi is also 0. And I'm integrating something that I don't really care what it is. So we end up getting a big 0. There. Okay? Questions? Okay, so on the exam, it may not always tell you to use Stokes' theorem to do stuff. Use divergence theorem to do stuff. So on those problems, you just start out by looking at what you are asked to do. If it looks awfully complicated, consider using one of those theorems to simplify what you have to do. Okay? So you may not always know beforehand if you want to use that theorem or not. Now here the clue, even if the problem didn't say use Stokes' theorem to find this, when I'm looking at this and I'm looking at the curl of that, that's already a very daunting task. So that's a good clue that you want to consider using Stokes. And remember, Stokes can go both ways. If you're asked to do a complicated line integral, perhaps you want to turn back to the curl of the field over the surface. All right, so we got that. The second one we'll look at, according to the list, is number 21. Find an equation of the tangent plane to the surface, something at some point. equation of tangent plane in general, if z is some function of xy, then it's z minus z0 equal to fx, x minus x0 plus fy, y minus y0. So that's the equation we want to use. And by the way, the normal vector of a tangent plane if you look at this, look at the coefficients here, the 1, fx, fy, but they're on different sides. So you can either write it as fx, well, negative fx, negative fy, 1, or fx, fy, minus 1. So those are the two vectors normal to any tangent plane if you're given a function f of x, y, z. One of them points up, one of them points down, or right and left, but they don't go in different opposite directions. Okay, so what we're trying to do here is to find this equation. Right? We need a few derivatives here. Let's solve for z. From here, we see z is equal to 2 minus 1/3 x squared minus 2/3 y squared under a root. The tricky thing here is potentially this can be positive or negative. And only one of them can be right. So how do we know which one it is? Where are we trying to find this tangent plane? Yeah, that's what we're trying to find, right? So this is the point we're trying to make the tangent plane. So if I'm putting x is equal to 1 and y is equal to 1, I better get z is equal to negative 1. Does that make sense? And you can see, obviously, the only way to make z negative 1 is to have the negative sign in front of the root. So therefore, we want to take the negative of these two signs. Make sense? Yeah? Good. Then we take our partials, which is not terribly hard to do. Looking at the bottom one there, fx, partial derivative of z with respect to x, the middle one, sorry, the one with the x in it. So minus 1/2, 2 minus 1/3 x squared minus 2/3 y squared to the negative 1/2. Then by the chain rule, we multiply by negative 2 over 3x. Right? That looks complicated, but we're going to plug in a point x is equal to 1 and y is equal to 1. We already know this stuff inside is going to be a 1. We just calculated that. So we're going to get minus 1 over 2 times minus 2 over 3, and that turns out to be positive 1 over 3, because that's a 1. Repeat that for y, partial with respect to y. Minus 4 over 3y. And fy at 1, 1, this is again a 1. So that's negative 1/2 times negative 4 over 3, and that's negative positive 2 over 3, sorry. Okay, then we use the equation z minus z0, fx, x minus x0, plus fy, y minus y0. So we get z minus the z point of the z component of the point is minus 1. Minus 1 fx, x minus 1, plus fy, y minus 1. And you can rearrange this a little bit to get the right form. All the forms are without fractions, so that's a clue. We want to get rid of the fractions. Let's multiply everything by 3. Multiply everything by 3, and then bring everything to one side. Bring the x, y, z to one side. I'm going to put them on the right-hand side. And then I'll put all the numbers on the, yeah. Z plus 1 multiplied by 3. Oh, so, gee, what am I doing? Yeah. There. Is that right now? Good, thanks. Oh, so that's a 6, right? Good. There we go. Much better. Okay, so the key thing here is that equation in the green box on the last page. That's the tangent plane equation. And also you need to know you may need to know the tangent plane normal vector. And that's either the negative x, fx, negative fy1, or positive fx, positive fy, negative 1. Okay? Okay, next one. What am I doing here? We're doing number 41. A wire lies on the xy plane along the curve. Y is equal to x squared. X is going from 0 to 2. Density of that wire is function of xy is equal to x. We're looking for the mass of this wire. Okay, so what we do here is you integrate along the length of that curve. So you do integration ds, little s for, because we're going along the curve, and we just carry the density along with us. And when we get all this together, we end up getting the mass of the wire. So let's first parameterize that curve. And remember, you can parameterize these things in any way you want, as long as the parameterization obeys the equation y is equal to x squared. So I'm going to make x is equal to t. And because y is equal to x squared, y is going to be t squared. And t is going to go from 0 to 2. So what's little d, d little s? Does anyone remember how we find that? That's the length of one tiny little segment of that wire. Very good. Magnitude of r prime dt, right? Because this is the magnitude of one tiny little segment of that wire. And you integrate along the entire thing, you get the entire length. And this time we're just carrying the density along with us. So r prime is just going to be 1, 2t, and we'll find the magnitude of that. That's simple. That's 1 plus 4t squared under a root dt. Now we integrate that. The parameter runs from 0 to 2. Yep, 0 to 2. Density is x, but x is equal to t in our parameterization. And ds is this thing right here. And we can integrate this by using a substitution. And this will end up being 17 u to the 1/2, 1/8 du. So that's u to the 3 over 2 times 2 over 3 times 1 over 8, 2 over 34, 1 over 12, I think. Yep. Okay, so that's 1 over 12 times 17 to the 3 over 2 minus 1, or 1 over 12 times 17, radical 17, minus 1. Questions? No? Okay. Well, that's the mass. What if you just wanted the length of that curve? You just integrate ds, right? You make that rho equal to 1, integrate ds alone. That'll give you the length of that curve. Okay, next one, number 22. Find an equation of the plane tangent to the graph, blah, blah, blah. we just did something very, very similar. So we're going to find the partials, evaluate at 2 comma pi. The slightly different thing here is that we don't have z, 0 right now. We're given x and y, we have to find that z. So from here, let's go find that number. If x is equal to 2 and y is equal to pi, and I'll put it into here, and I will get 4 pi plus 2 pi. That's sine of 6 pi. That's a 0. So that means z, component of that point, is equal to pi. Let's find the partials. So I got these from here, and then that gave me this back here. That's the reasoning there. Fx, let's see, that's gone. So here we're going to get cosine pi x squared plus 2y times the derivative of this, and that's 2 pi x. Evaluate at 2 comma pi. We get cosine of 6 pi. That's a 1, right? 1 times 2 pi times 2, that's 4 pi. Repeat that for y. Cosine pi x squared plus 2y times derivative with respect to y, that's a constant, and we get a 2 out of this. Fy of 2 comma y is cosine of 4 pi plus, we already did that, cosine of 6 pi, that's a 1, so that's a 2. Therefore, the equation z minus pi is equal to 4 pi x minus 2 plus 2 y minus pi. Rearrange a little bit. 4 pi x minus 8 pi plus 2y minus 2 pi. Let's bring x, y, z to one side and everything else to the other. So we're going to get 10 pi here. Going over here, subtracting 1 is 9 pi. All right? Very similar to the previous one we just did. Same equation, same process. So if a tangent plane problem were to show up, it should be, you shouldn't get it wrong, okay? Oh, by the way, every single question will be weighted the same, 10 points. So if you really have truly no clue how to do something, but you have some idea how to do some other stuff, spend your time on the stuff that you know how to do. If you have to guess on something in the end, guess, because everything is weighted the same. Don't let one problem kill all the time you got. The problems are not necessarily arranged in the order of difficulty. So please budget your time accordingly. If you do a practice exam under real exam condition, that'll give you a little bit of taste of that too. Okay, so anyway, where were we? We did 22, right? So next one, 43. Evaluate the line integral x dx plus y dy plus xy dz, where c is parameterized by this cosine of ti plus sine t j plus cosine t k. And t is from minus pi over 2 to 0. Okay? All right, so first of all, you want to remember, this is just a really, really fancy way to write f dot dr. Where f is equal to x, y, xy, and r is equal to x, y, z, right? That's just this. Another way to write f dot dr with f being that, r being this. Now we already have this curve parameterized. So we're going to let x be cosine t, y be sine t, and z be cosine t, because this and that are the same thing. And that means we can also use these three things here to rewrite f, and just do an f dot dr. So f turns into cosine, sine, xy will be cosine and sine. And then dr, looking at the given parameterized curve, is negative sine, positive cosine, and then negative sine. dt. T again is going from minus pi over 2 to 0. Then we integrate f dot dr. So we get negative pi over 2 to 0. These two things dotted together. So we get negative cosine sine plus cosine sine, and those cancel. Minus cosine sine squared dt. Keep in mind that whenever you're dealing with trig stuff, things can often look really, really complicated, but often there's always a way to make them look much nicer. Here we don't have to do too much. These two first things just go away, and then we're going to end up integrating this, and that's very easy to do. Another substitution will do it. Let u be sine and du is cosine. So this will turn into sine of negative pi over 2 is negative 1. Sine of 0 is 0. And that's a u squared. Cosine t dt is du. So that's negative du. Negative u cubed over 3 minus 1, 0. So we're going to end up getting 0 minus minus, that's plus, and then this might be minus again, so minus 1/3, is that right? I don't have the answer marked here. Let me check. Yep, that's right, minus 1/3. Okay there? Got it? Good. Questions on this one? All right, what time is it? Okay, let's keep going. We got time for, I think, a couple more. 47. Another f.dr. We've done a ton of these things, so you should be ready for this. C is the circle of radius 1. Centered at 1, 2, oriented counterclockwise. So that's a circle we're dealing with, and it's going this way. All right, so we can parameterize this. What's another option? Rings, very good. Green's theorem says that f.dr, remember Green is just a special case of Stokes, but Green is for a two-dimensional with the, everything happened on the xy plane, which is what we got here. Qx minus py, right? dA, where the vector field is given as pq, sorry. And by the way, remember this is just the same as curl of f dot n. So this is really Stokes, but with the surface being on the xy plane. Here, p is equal to xy squared minus 1. Q is equal to x squared y minus x. Qx, partial derivative, is 2xy minus 1, right? And py is 2xy. Therefore, here we're going to end up doing a double integral over the region D, which is this guy right here, of qx minus py minus 2xy minus 1 minus 2xy is negative 1 dA. Minus 1 is a constant. That's minus 1 times double integral over d dA. And what's this? Geometrically, what is this asking? The area of D, area of a circle radius 1, that regardless where the center is pi r squared, right? As usual, doesn't matter, the center doesn't change anything. So circle radius 1 is pi r squared, pi 1 squared pi, minus 1 times pi, so negative pi. Now the harder way is to parameterize that circle. R of t is equal to blah, 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 and do an f dot dr. And it gets quite complicated. In the end, you get negative pi, of course, but it gets pretty complicated. Green's theorem makes things almost laughably easy, almost. Questions? Okay, I think we got time for one more, so let me find what the next one is. 38. A says that D is the solid region above the xy plane that's between z is 4 minus x squared minus y squared and z is equal to 1 minus x squared minus y squared under a root, then triple integral over d of x squared plus y squared plus z squared under a root, dv is equal to question mark. Okay, now I'm going to ask you this. What shape is this? The whole sphere? Upper sphere, right. Upper hemisphere of what radius? 2. How about this guy? Radius 1, same thing, upper hemisphere. So what coordinate system should we be looking at? Absolutely, spherical. Radius 1, radius 2, okay, so then stuff is bounded between these two hemispheres. We're going to be integrating in spherical, so let's set up the bounds first. How should theta be bounded? Theta is the angle on the xy plane, right? 0 to 2 pi, that's right. We want the entire, all the way around the xy plane. So all 0 to 2 pi. Remember, this is how we measure theta. We want it to go all the way, that's enough stuff on there, 0 to 2 pi. How about phi? How should it be bounded? 0 to pi over 2, very good. Right? Because phi starts from the positive z-axis down. We want to start accumulating at z, positive z. We end the accumulation at the xy plane. So we stop at pi over 2. How about rho? 1 to 2. We want everything between hemisphere radius 1 and hemisphere radius 2. What's x squared plus y squared equal to z squared in spherical? Rho squared. Good. So therefore, the triple integral of d of x squared plus y squared plus z squared dv will be 0, 2 pi, 0 pi over 2, 1 to 2. This is rho squared, so that's a rho then. And what's dv? Rho squared sine phi d rho d phi d theta. And because all of these three are bounded by constants, the order is irrelevant, but this is a pretty standard order that we deal with these things. I think sometimes we integrate phi last, but it's irrelevant. And what's left here, this is just trivial integral from this point on. So it's equal to whatever it's equal to. 15 pi over 2 or something like that. Yeah. All right, we are out of time. Okay, so don't forget, exam is Tuesday, 1 p.m. Okay, Tuesday, 1 p.m. I will be available next week, Monday. Even though regular office hours are not in effect, I will hold my regular office hours on Monday. I'll be available Tuesday morning too, okay? So, study well. See you next week.
Just plus 1 is a negative line. What do you define? What is the boundary here?
I don't, well, you can set up a bounds, all that, but remember, this is just asking for the area of the region T.
Okay.
We know it's a circle.
Okay.
So why do the hard way?
Okay. Right? If we want to set up boundary, what is going to be the boundary? Is the radius 0, 1, and then?
Well, you have to parameterize this thing here, and then in this case, the parameterization will be cosine t plus 1, comma, sine t plus 2.
Oh, okay.
And in that case, t will go from, I'm sorry, it'll be r cosine t, r cosine theta or whatever, plus 1, and r sine theta plus 2. Theta will go from 0 to 2 pi. Theta is still measured this way.
Okay.
And r will go from 0 to 1.
Yeah.
So we're going to measure that from the center of that circle in that case.
Thank you. Would there be a pi squared?
Pi square where?
Because it's from like 0 to 2 pi into, it will be pi by 2 into 2 pi, right?
No, because there is a sine pi there. If you integrate sine pi 0 to 2 pi, there won't be pi left.
I was wondering, for the tangent plane equation, you have the tangent plane equation, but couldn't you just do the del vector?
Sure, yeah, it's the same thing, yeah.
Okay, cool. And then, are you available anytime today?
I am.
For office hours?
I have my regular office hours.
Okay, when are they?
9 to 11.
Okay, thank you.
Let's talk outside so the next class can start.